First, for each video in which you see a brief pause in the beginning before I step into frame, that indicates that we don't yet have a battery for the remote, so I've got to step back and forth to the camera. Now, for each of these points, for basically each video, the good you can get out of this will come after you've at least read the chapter, hopefully have tried a few of the problems. So these are for after reading, not before. Or instead of. If you skip one of those things, you'll have a problem. For example, I'm going to start with the realization that from last time, or last chapter, chapter 14, typically covered right before chapter 20 in this series, we describe harmonic motion as some displacement as a function in time. Now, each one of these things is important. We're going to shift our notation a couple of times at a couple of different places for what I really hope seems to you like good reasons. It seemed to us, it seemed to the authors to be good reasons. Here, this is a displacement in time for oscillation, the work of chapter 14. This is one-dimensional motion. So oscillation as a function of time is given by some amplitude A, the maximum range of that oscillation, times the cosine. Now, in oscillation, we were just looking at this as a function of time, because the central point, our starting point, was typically defined as 0. So the oscillation just depends as a function of time. Again, this is omega, this is not W. Omega, the Greek letter, times time, perhaps some phi naught, some phase shift. Now, in oscillation, we work with this equation, starting with the sine function that is the cosine, because typically as that's drawn, let me just peek to make sure that, oh good, I'm filling my memory of the board width is working. If I take a mass on a spring, say, which is the example that we used, mass on a spring, a simple pendulum, either way you displace that, release it, and acting under that centrally directed force, trying to pull it back toward equilibrium, it'll then tend to swing through equilibrium, but that means it will start off at its maximum value. The way that the cosine function starts off at its maximum value. Now, for sinusoidal waves, we're going to use, like we did before, we're going to use the sine function. Ah, but this is the cosine. They're the same thing. A shift of starting point, the sine and the cosine are exactly the same thing. When I talk about sinusoidal functions, that includes the sine, it includes the cosine, heck, it includes the tangent. So we're going to write this as some displacement. Now, there are different types of waves. We'll talk about that very shortly. Or it'll be covered in one of the other videos. So I'm just going to write d as the displacement. Maybe it's in the x direction, maybe it's in some direction perpendicular to the direction of motion of the wave. So it's a function of x, and x is the direction the wave is traveling along. Maybe not the particles. That depends on which direction D is in, or what D really represents. We'll have to see in each individual case. But it's a function of some variable in the direction of motion and a function of time. Now, in this case, if I were to set up a sine wave as before, the sine wave starts at 0 and oscillates back and forth between some amplitude function, some maximum value, so that will still remain as the amplitude, times the sine. Now, in this case, this wave is not only changing through time, but it also represents something that's moving through space. So we can't just pick and say, it's not just a function of time, it's also a function of space. Some function k x minus omega t plus possibly some phase shift. Now, let me hit each one of these briefly. K, and you see we are now at the point, this is why I was pounding the drum for omega here, and as opposed to just calling it the Latin letter it kind of looks like, because we have a very limited number of letters to give to a tremendous number of variables. So that's why I would use Ks to represent the spring constant, because lowercase k is also used to represent what's called the wave number. And in this case, the wave number is taking this position, something in space, which has units of length, and taking those units of distance away. After all, the sine of some number has to be at the sine of some angle. There is no variable or no quantity we're going to see whose units are like meters times the cosine of seconds. If you've got units that aren't units of degree inside some sine or cosine, something's gone wrong, stop, go back, find out what that was. That will help you. The wave number is defined as 2 pi over the wavelength. Now, the wavelength we've already seen discussing oscillation. The wavelength is the distance from one point on a wave to that same point on the next wave. That is one wavelength lambda. And if I were to take this point, it's not this point, that's not the same. It's at the same displacement. But here, it's at this displacement going up, whereas to be the same point, it's got to be at this displacement going down, also lambda, and so on. And what this is doing is you'll notice that it's taking x over lambda is some fraction of a wavelength, and then multiplying it by 2 pi is some fraction of a full cycle. After all, when this wave is gone, one wavelength, it's gone, it will have gone through one full cycle, or 2 pi radians. So if x is lambda, lambda over lambda is 1, kx will simply be 2 pi. We've seen in our discussion of oscillation that omega is the angular frequency, or 2 pi times the frequency, where, again, as we've seen in our discussion of oscillation, the frequency is 1 over the period, where the period is the time that it takes to move through, the time that it takes for one full wavelength to pass by a given point. Now, this sign is important. If I have negative omega t, what that negative sign is telling us is that the wave is traveling toward positive infinity. So kx minus omega t means that a wave starting from negative infinity toward positive infinity. If I were to write a sine kx plus omega t plus that phase constant phi naught, I would be looking at a wave starting at positive infinity going to negative infinity. So positive omega t, the wave is traveling toward negative infinity. Phi naught, as in oscillation, represents some phase constant, because who knows? Perhaps we're comparing two different waves. Perhaps something's happening. We aren't able to define the time equals 0 in a nice, convenient fashion, so we need to account for some shift in time. Those things could happen. And all of these things together represent the phase of the wave. So that's how the wavelength, which is mixed in with the wave number, and the frequency, which is mixed in with the angular frequency, relates with the phase, which is everything in parentheses. The sign of whatever here is the phase.